Hey everyone, welcome back to my channel. In the continue of the previous video where we talked about the descriptive statistics in machine learning, today we're going to go a bit deeper. We're going to talk about the shape of your data before running the ML models. We'll see why a normal looking histogram makes life easy, why skew or heavy tails can run models, and how one or two weird points, which are called outliers, can pull your whole results off track. So stick around, this will save you hours of debugging. First, let's see what do we mean by distribution anyway. In the previous video, we talked about the spread of our data and mentioned that we could check it by standard deviation and range. We also point at skewness and kurtosis to understand shape. Now we want to drill this part a bit more. A distribution describes how values of a variable are spread across possible values. Distribution gives us the full picture of how all values occur, gives us shape, symmetry, peaks, tails, skewness, and outliers. For example, if test scores cluster around 75, that's one shape, and if they cluster at the top and tails off slowly, that's another shape. So understanding this is the first step to choosing the right model and transformation. I always tell my students, think of the distributions as reading the DNA of your variable. So let's look at the three common shapes you'll actually meet. First one is normal distribution. It's symmetric, most values are near center, and it's great for many methods. It is also called bell distribution because, as you can see, the shape of the distribution is like a bell. Second type is skewed. In skewed, one side is stretched out, as you can see here. This is an interesting type because many real-world measures like income or minutes of practice are skewed. And the last distribution type is heavy-tailed. In heavy-tailed distributions, extreme values occur more often than a normal curve would predict. I would say think of examples like insurance claims or viral social media posts. So in general, each of these shapes has practical consequences for modeling, so I suggest you never ignore them. Now, next question is that how do these shapes matter for common models? Let's make that concrete. Let's start with normal shaped distributions. As you may know, a lot of classical statistical tools assume normality at some level, but not always for the raw variable, often for residuals or the errors. When those errors are normal, the math that gives us p-values and confidence intervals behaves well. So that's why normality is often mentioned in textbooks, because it makes inference reliable and interpretable. But we all know that real data are not always so cooperative. That's where the second shape occurs. By skewness, we mean that if a variable is skewed, the mean gets pulled toward the tail. So that can mislead you, because in this case, the average person might not be a representative of the whole data set. In models that optimize squared error is a concept that is used in regression models. So in models that optimize squared errors, like OLS regression, heavy skew inflates error for far tail points and pulls the fit around them. So it can be misleading. But what can we do about skew? I'd say transformation are one fixed common. Practical ways to handle skew are: first, apply a logarithm function or square root transformation to compress the tail. Second one is use boxcogs to find the best transformation. And lastly, fit robust models because they're less sensitive to tails. Or use ranked-based methods, for example, Wilcoxon. We use these models because we need inference without strong assumptions. The right choice out of these options, I'd say, depends on your goal, so you can choose any of them. depending on which goal you choose for your dataset. Next shapes are heavy tails, and I'd say they are trickier compared to skewed ones. Heavy-tailed distributions produce extremes far more often than a normal curve suggests. For models, that means sudden, dramatic errors. For example, if you train a model assuming normal-like errors, heavy tails will make it unstable. We have some solutions to handle heavy tails distributions. For now, I just mentioned one of them, and later in other videos we will hopefully talk about more of them. For now, we are using alternative loss functions. Loss functions are important parts in machine learning algorithms, which we'll catch up on that too in the future videos. So anyway, as I was saying, one solution to handle heavy tail distributions data before running the ML model is robust loss function. Like Huber loss, they don't let single big errors, which are common in heavy tail distributions, dominate training. So now that we understand the importance of data distribution and considering it before building the model, let's talk about the single most dangerous thing in a dataset: outliers. An outlier is an observation that stands away from the rest. Not all outliers are bad, sometimes they're real discoveries, but sometimes they're errors. Errors like typos, measurement faults, or data entry glitches. The key to consider whether an outlier is important or not is the influence. You should ask, does that point change my model? Because sometimes a single outlier can drastically alter slopes, coefficients, and predictions. So now let's see, how do we find them and how do we decide what to do? Start simple. Histograms and box plots often reveal outliers quickly. For numeric cutoffs, z-scores or the IQR rule can help you find out outliers. For example, we have this dataset, and z-score tells you how many standard deviations a value is far from the mean. So the formula is z equals x minus x bar divided by a standard deviation. As I said, x bar is the mean and s is the standard deviation. So we say that the absolute value of z greater than 3 are considered outliers. Let's say x bar equals 80.15 and standard deviation equals 19.5. To calculate z-score for the data of 150, we use the formula and it'll give us z equals 3.58. And since the absolute amount of 3.58 is greater than 3, we conclude that 150 is an outlier by z-score rule. As I said, another way for finding outliers is using the IQR rule. So for finding outliers through IQR or interquartile range, we focus on the middle 50% of the data. IQR equals Q3 minus Q1. Q1 is the first quartile or the 25th percentile. For example, let's say here is 68.5. And Q3 is the third quartile or 75th percentile. And it is here 86.5. Then IQR would be 86.5 minus 68.5, which gives us 18. So outlier cutoffs would be Q1 minus 1.5 IQR for lower limit and Q3 plus 1.5 IQR for upper limit. And we have the range of 41.5 and 113.5. This range means that any value above 113.5 or below 41.5 is an outlier by IQR rule. Now that we have found outliers, what are the principled options? You need to handle outliers carefully. First, investigate if it is a data entry error or not. If it is, so fix it. Second, if it's genuine but rare, you can transform, for example, using log or use robust algorithms that downweight streams. And lastly, you can remove them, but I warn you, it is not that simple. Maybe you can do it if they are the result of measurements or recoding issues, or when they come from a different population than the one you're already working with. So there is no way you can just get rid of them easily without any convincing reason. So anyway, let's connect distributions and outliers to model behavior. You see some consequences of these investigations. OLS regression can shift dramatically with outliers. For classification models, skewed class distribution shifts thresholds and metrics, so you can get misleading high accuracy. Be careful with that. And for tree-based methods, they are more robust to outliers, but Skew can still bias split points and feature importance. So understanding distributions saves you a lot of trial and errors and wasted computation. Before we finish, I'll give you a simple checklist you can run on any dataset. First, plot a histogram and box plot for key variables. Then compare mean and median to see if there is any big differences and look for a skew. Third, compute skewness and IQR. And next, flag extreme z-scores and IQR roll points. And finally, if issues exist, then try transformations or robust methods before you declare a model is the final model. So to wrap up, always check your data shape first. Normality is nice, but skew and heavy tails are common. Outliers may be errors or important discoveries. Use transformations, robust methods, or ranked-based tests when needed. In the next episode, we'll study correlation and causation and why feature selection can mislead you if you don't think statistically. And that was it. If you found this video helpful, please like and subscribe, and tell me in the comments which dataset I should use demo these checks.